This Java applet showing a simple demonstration of Ohm's law. The green color indicates positive voltage, and the gray color indicates ground, or earth. The movement of yellow dots indicates current, in the conventional direction. Current flows from a positive voltage source through one of two resistors to ground. The amount of resistance in ohms is shown to the right of each resistor. The voltage can be controlled using the voltage slider at right. By Ohm's law, the current through each resistor will be equal to the voltage divided by the resistance. The resistor at right has 10 times as much resistance, so it will have 1/10 the current. Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. Introducing the constant of proportionality, the resistance 1 arrives at the usual mathematical equation that describes this relationship to I equals V/R, where I is the current through the conductor in units of amperes, V is the voltage measured across the conductor in units of volts, and R is the resistance of the conductor in units of ohms. More specifically, Ohm's law states that the R in this relation is constant, independent of the current. Ohm's law is an empirical relation which accurately describes the conductivity of the vast majority of electrically conductive materials over many orders of magnitude of current. However, some materials do not obey Ohm's law. These are called non-ohmic. Ohm relationship. By knowing any two values of the voltage, current, or resistance quantities, we can use Ohm's law to find the third missing value. Ohm's law is used extensively in electronics formulas and calculations, so it is very important to understand and accurately remember these formulas. It is sometimes easier to remember this Ohm's law relationship by using pictures. Here the three quantities of V, I and R have been superimposed into a triangle, affectionately called the Ohm's law triangle, giving voltage at the top with current and resistance below. This arrangement represents the actual position of each quantity within the Ohm's law formulas. Ohm's law triangle. Transposing the standard Ohm's law equation above will give us the following combinations of the same equation. Then by using Ohm's law we can see that a voltage of 1 V applied to a resistor of 1 ohms will cause a current of 1 A to flow, and the greater the resistance value, the less current that will flow for a given applied voltage. Any electrical device or component that obeys Ohm's law, that is, the current flowing through it is proportional to the voltage across it, I alpha V, such as resistors or cables, are said to be ohmic in nature, and devices that do not, such as transistors or diodes, are said to be non-ohmic devices. Electrical power in circuits. Electrical power, P, in a circuit is the rate at which energy is absorbed or produced within a circuit. A source of energy such as a voltage will produce or deliver power while the connected load absorbs it. Light bulbs and heaters, for example, absorb electrical power and convert it into either heat or light, or both. The higher their value or rating in watts, the more electrical power they are likely to consume. The quantity symbol for power is P and is the product of voltage multiplied by the current, with the unit of measurement being the watt, W. Prefixes are used to denote the various multiples or submultiples of a watt, such as milliwatts, MW equals 10-3 W, or kilowatts, kW equals 103 W. Then by using Ohm's law and substituting for the values of V, I and R, the formula for electrical power can be found as. Again, the three quantities have been superimposed into a triangle, this time called a power triangle, with power at the top and current and voltage at the bottom. Again, this arrangement represents the actual position of each quantity within the Ohm's law power formulas. The power triangle. And again, transposing the basic Ohm's law equation above for power gives us the following combinations of the same equation to find the various individual quantities. So we can see that there are three possible formulas for calculating electrical power in a circuit. If the calculated power is positive, plus P, in value for any formula, the component absorbs the power, that is, it is consuming or using power. But if the calculated power is negative, P, in value, the component produces or generates power, in other words it is a source of electrical power such as batteries and generators. Electrical power rating. Electrical components are given a power rating in watts that indicates the maximum rate at which the component converts the electrical power into other forms of energy such as heat, light, or motion. For example, a 1/4W resistor, a 100W light bulb, etc. Electrical devices convert one form of power into another. So for example, an electrical motor will convert electrical energy into a mechanical force, while an electrical generator converts mechanical force into electrical energy. A light bulb converts electrical energy into both light and heat. Also, we now know that the unit of power is the watt, but some electrical devices such as electric motors have a power rating in the old measurement of horsepower or HP. The relationship between horsepower and watts is given as 1 HP equals 746 W. So for example, a 2 horsepower motor has a rating of 1492 W, 2x 746, or 1.5 kilowatts. Ohm's law pie chart. To help us understand the relationship between the various values a little further, we can take all of the Ohm's law equations from above for finding voltage, current, resistance and of course power and condense them into a simple Ohm's law pie chart for use in AC and DC circuits and calculations as shown. Ohm's law pie chart. As well as using the Ohm's law pie chart shown above, we can also put the individual Ohm's law equations into a simple matrix table as shown for easy reference when calculating an unknown value. Ohm's law matrix table. Ohm's law example No. 1. For the circuit shown below, find the voltage, V, the current, I, the resistance, R, and the power, P. Power within an electrical circuit is only present when both voltage and current are present. For example, in an open circuit condition, voltage is present but there is no current flow. I equals 0, 0, therefore V asterisk 0 is 0, so the power dissipated within the circuit must also be 0. Likewise, if we have a short circuit condition, current flow is present but there is no voltage. V equals 0, therefore 0 asterisk I equals 0, so again the power dissipated within the circuit is 0. As electrical power is the product of V asterisk I, the power dissipated in a circuit is the same whether the circuit contains high voltage and low current or low voltage and high current flow. Generally, electrical power is dissipated in the form of heat, heaters, mechanical work such as motors, energy in the form of radiated lamps, or as stored energy, batteries. Electrical energy in circuits. Electrical energy is the capacity to do work, and the unit of work or energy is the joule, J. Electrical energy is the product of power multiplied by the length of time it was consumed. So if we know how much power, in watts, is being consumed and the time, in seconds, for which it is used, we can find the total energy used in watt seconds. In other words, energy equals power x time and power equals voltage x current. Therefore electrical power is related to energy and the unit given for electrical energy is the watt seconds or joules. Electrical power can also be defined as the rate by which energy is transferred. If 1 joule of work is either absorbed or delivered at a constant rate of 1 second, then the corresponding power will be equivalent to 1 watt, so power can be defined as 1 joule/sec equals 1 watt. Then we can say that 1 watt is equal to 1 joule per second, and electrical power can be defined as the rate of doing work or the transferring of energy. Electrical power and energy triangle. Or to find the various individual quantities. We said previously that electrical energy is defined as being watts per second or joules. Although electrical energy is measured in joules, it can become a very large value when used to calculate the energy consumed by a component. For example, if a 100-watt light bulb is left on for 24 hours, the energy consumed will be 8,640,000 joules, 100 Wx 86,400 seconds, so prefixes such as kilojoules, kJ equals 103J, or megajoules, mJ equals 106J, are used instead, and in this simple example, the energy consumed will be 8.64 mJ, megajoules. but dealing with joules, kilojoules, or megajoules to express electrical energy, the maths involved can end up with some big numbers and lots of zeros, so it is much more easier to express electrical energy consumed in kilowatt hours. If the electrical power consumed, or generated, is measured in watts or kilowatts, thousands of watts, and the time is measured in hours not seconds, then the unit of electrical energy will be the kilowatt hours, kilowatt hour. Then our 100-watt light bulb above will consume 2400 watt-hours or 2.4 kilowatt-hour, which is much easier to understand the 8,640,000 joules. 1 kilowatt-hour is the amount of electricity used by a device rated at 1000 watts in 1 hour and is commonly called a unit of electricity. This is what is measured by the utility meter and is what we as consumers purchase from our electricity suppliers when we receive our bills. Kilowatt-hours are the standard units of energy used by the electricity meter in our homes to calculate the amount of electrical energy we use and therefore how much we pay. So if you switch on an electric fire with a heating element rated at 1000 watts and left it on for 1 hour, you will have consumed 1 kilowatt-hour of electricity. If you switched on 2 electric fires each with 1000 watt elements for half an hour, the total consumption would be exactly the same amount of electricity, 1 kilowatt-hour. So, consuming 1000 watts for 1 hour uses the same amount of power as 2000 watts, twice as much, for half an hour, half the time. Then for a 100-watt light bulb to use 1 kilowatt-hour or 1 unit of electrical energy, it would need to be switched on for a total of 10 hours, 10 x 100 equals 1000 equals 1 kilowatt-hour. Now that we know what is the relationship between voltage, current, and resistance in a circuit, in the next tutorial relating to DC circuits, we will look at the standard electrical units used in electrical and electronic engineering to enable us to calculate these values and see that each value can be represented by either multiples or submultiples of the standard unit. Use Ohm's law calculator. Calculate power, current, voltage or resistance. This is showing a simple resistive circuit. The green color indicates positive voltage, and the gray color indicates ground, or earth. The movement of yellow dots indicates current, in the conventional direction. The left side of the circuit shows a voltage source providing 5 volts, and the current flows through a number of switches and resistors to the right. The amount of resistance in ohms is shown to the right of each resistor. To turn a switch on or off, just click on it. If you move the mouse over any component of the circuit, you will see a short description of that component and its current state in the lower right corner of the window. If there is only one switch closed on top and one closed on the bottom, then there is a single path through the circuit, and by Ohm's law, the current will be equal to 5V divided by the total resistance through the current path. If there are multiple current paths, you may have resistors in parallel.